Hello my fellow developers, I'm glad that you decided to use Postgres for your generative AI applications. And in this video I will show you how to use the pgvector extension of Postgres in practice. This extension provides Postgres with all the essential capabilities needed from vector databases. Alright, let's not waste a minute and do a deep dive. As developers, we tend to learn frameworks, libraries and other technologies by building sample applications. Plus, in the Python universe, we can take advantage of Jupyter notebooks. That's why for this video I contributed a Postgres pgvector notebook to the OpenAI cookbook repository. And right now I will walk you through this notebook so that you can understand how to use Postgres pgvector in practice for your Python GenAI applications. I have already downloaded this OpenAI repository to my local machine and ready to get started. Prerequisites. I'm going to start Postgres in Docker, that's why I need to have a Docker installed on my machine, and I encourage you to do the same. But if you wish to start the database by other means, feel free to do that. Then certainly we need to have Python and pip to install required modules, and OpenAI API key is required because we are going to use the OpenAI embedding model to generate embeddings for your user prompts. Okay, step number one. We need to install the following three libraries. The first one is OpenAI, and that OpenAI library allows you to connect to the OpenAI embedding API and generate a vectorized representation for the user prompts that this Jupyter notebook will be using. Then you know that we will use Postgres pgvector and we will store some sample dataset with some sample embeddings in the database, and psychopg2 will be used as a driver for Python apps. And lastly, we need Wget to download some sample dataset from the Hugging Face portal. Let's move forward, my friends, and install the required modules. Wonderful, it's ready. Next, I want to start my Postgres instance. And as I said, there are many ways to start Postgres, but I as a developer like to use Docker. So let's go ahead and start Postgres in Docker. And right now you can see that the Jupyter notebooks pulls various images and downloads them on my local machine. While this is happening, let's jump to the Docker compose YAML file. What happens here? I'm going to use this image and pgvector. This image comes with the core Postgres modules plus the pgvector extension. Once that container is started, it's going to run on your machine in Docker, and that's going to be the container name and some other parameters. Jumping back, we successfully created their network and we have the Postgres container running. Next step, what we want to do. In these instructions, we are going to use the pg_is_ready command to make sure that Postgres is ready for all the incoming connections and application requests. Because when you start Postgres for the very first time, the database needs to initialize itself. That's why we are checking this. And once the database is ready, we will also connect to the Postgres container. We will start this PSQL tool that comes with every Postgres distribution, and we will enable the Postgres pgvector extension. To do that, you need to execute this create extension vector command. Moving forward. Okay, you can see that now Postgres instance accepts all the connections. We successfully connected to it and enabled the vector extension. Alright, the Postgres is up and running and ready for our experiments. What's next? As I said, we are going to use the OpenAI embedding model. You need to create an OpenAI key. Let's start it, and you will see this prompt. I need to provide my API key. Alright. Ready? Provided, the OpenAI API key is set. Everything is ready. Next step is we need to load the sample dataset. Let me click the start button and I will give you more details on this data. So that's a movies dataset that comes with more than 45,000 different movies. You will find many blockbusters that I bet you watched in the past from various studios including Disney, Warner Brothers, Paramount Pictures and many more. This dataset is large because it comes with pre-generated embeddings. Today in our application code we will be using this OpenAI text embedding ADA002 model, and what I've done, I took this dataset and every movie has an overview, and for every overview I generated a corresponding embedding using this model. The dataset is downloaded and you will find it on your local operating system under this notebook folder. Next, I want to use the Postgres driver to connect to my Postgres instance. Open this cursor. That's what I want to do. Okay, the connection was successful. First, we will connect to Postgres and we will open this movie schema SQL file. Let's take a look at it, what's inside. That's a simple schema file. It will create this table movie. And that's a pretty big table. For instance, what's interesting for our experiments, every movie has an overview. And then every movie has a corresponding overview vector column. And that stores an OpenAI vector. Every OpenAI vector has 1536 dimensions. Jumping back to the notebook, and once the schema, the table is created, we will load the data. And once all the data is loaded, I will execute this select count command. I just want to see how many rows we have in the table. It will take around a minute to load this dataset because it comes with embeddings, and embeddings take space. So let's wait. Wonderful, the data was loaded, and you can see that we have over 45,000 movies loaded with various embeddings. Also, let me jump to data grip and show you how the data looks like. That's my Postgres connection. Those were my Postgres connection properties. Let me test the connection. Yep, I can connect to the database. Let's do this. And now if you go to the schema, you will find this movies table. Let's select title, overview, and overview vector from movie table. And I want to show you just 3 random movies. So here is how it looks like. You can see that various movies and long overviews. And for every overview, we have a corresponding vector embedding. Going back to our Jupyter notebook, everything is ready for the vector similarity search in Postgres. However, before I run my first similarity search request against the database, I want to add 3 additional functions to my Python application. The first one is the get embedding function. It takes the user prompt and then makes a call to the OpenAI embeddings API to generate an embedding for the provided user prompt. And this is the model that we are going to use for this generation. Once the vector is received from OpenAI, we will convert it into their string and then return it to the application logic that executed this method. In addition to that, another function is called getMatchingThreshold. That one is used to fine-tune your similarity search. So this threshold is the value in the range from 0 to 1, or think like from 0% to 100%. And in my case, I will be returning those movies that are 70 or higher % close to the provided user prompt. Okay? And the last function is the getMatchingCount. Basically, how many movie recommendations do you want your logic to return? In my case, I will be returning just 3 movies. It's more than enough to make a choice. Nice. Here is our first user prompt. Some user wants to watch a movie about a space adventure. That's a nice choice. We'll take this user prompt and then we will make a call to our getEmbedding function that we have just discussed. The function will return us this vector, this embedding. And after that, we will use our cursor that has a connection to the database, and we will ask Postgres, please return the title and the overview from this movie table. What happens here in this where clause? Let's break this down into pieces. First, we are calculating the distance between the overview vectors of the movies and the provided user prompt. We are using the cosine distance operator. The cosine distance is the angle between your user prompt and your movie overview. The smaller the angle, the more relevant the movie would be for the user prompt. And that's the distance, that's the angle, but then we want to use our matching threshold. We want to use the similarity. That's why we are taking this distance and we are subtracting it from 1. And then we will compare it to our matching threshold, to this value. We are going to return only those movies that are bigger or equal to 0.7. Finally, we are going to order all the movies by their distance between the overview vector and the user prompt vector. And then we are returning 3 movies for every user request. Nice. Once the data is back to the application, we will print it to the terminal, or you can then send it back to your front end, to your UI, and display for the user. Let's run this request. And you can see 3 movies for the provided user prompt. Wonderful. You have the title and you have an overview. Next, let's talk about data pre-filtering. When we are performing the vector similarity search, we are running a quite expensive operation in the database because those vectors are multidimensional arrays, and we are taking a user vector and we are comparing it to all the vectors of your data set. It's quite expensive. That's why it's useful to pre-filter your data before you start doing the vector similarity search. And Postgres, as a general purpose relational database, comes with various functions and data types that will help you to pre-filter your data before the similarity search happens. Imagine that you're building that movie application, you have that UI where the user can pick a movie category, the movie rank, etc. And that certainly will help you to pre-filter your data before you run the similarity search. We have the same user prompt, a movie about a space adventure. However, the SQL request looks a little bit different. This time we are getting the title, vote of the movie, its genre, from the same movie table. However, first we will pre-filter. We want the database to return only those movies that have the rank 7 or higher. And plus, the user said that he is interested in the science fiction movies. And only after that we are going to run this vector similarity search. Let's execute this logic and see how the result changes. You see that their database recommends you to watch Interstellar. Yeah, that was a wonderful movie. And the other two on the Silver Globe and Forbidden Planet. Next, I want to make sure that the data gets in fact pre-filtered before the similarity search happens. How can we do this in Postgres? You just need to take a look at the execution plan that is generated and selected by the database. Just add this explain command to our original select request. Let's run this operation to get the execution plan. And in Postgres, we need to run the plan from the bottom up. So what happens first? We are doing the sequential scan on the movie table. And first, we will pre-filter the data by the rank. Then we will pre-filter the data by its genre. And only then, in the end, we will get the records that are close to the provided user prompt. And finally, then we are sorting this data by displaying the most relevant movies to the user. Wonderful. Next, let's talk about various optimizations. As the previous execution plan showed, by default, the database performs the full sequential scan over your dataset. And that can become a bottleneck if you store hundreds of thousands or millions of embeddings in your database. However, you can index embeddings, and Postgres certainly supports various index types for your vectorized data. What we are doing next? Let me take a look at the execution plan one more time, and here is we are performing just the similarity search. We are not pre-filtering the data. Yes, the database performed the sequential scan to find the most relevant movies for the provided user prompt. Postgres pgvector supports 2 indexes at the moment. The first one is IV flat and the second one is HNSW. And the second one is the most widespread and the most promising index type across all the vector databases. And it also supported by Postgres. I'm going to connect to the database and I want to add this HNSW index there. Let me run this request. So this HNSW stands for the Hierarchical Navigable Small World Index. And if you're not familiar with this index type, just find a special video on my YouTube channel where I broke down this index in pieces. Once this index is created, we will rebuild the database statistics and then we will print this data. Wonderful, the index is ready. Now, if you scroll down this notebook, we will get to this final code snippet where we can run the same request that we executed before to check what's the execution plan right now after the index is created. Let's run it. And you can see that right now we are performing the index scan over this vectorized data. Job done with the index. Even though we came to the end of this Jupyter notebook, my friend, I want to briefly introduce you another optimization technique in the Postgres ecosystem. Let's say that you want to scale horizontally. For instance, you store millions of different embeddings and they no longer fit on a single database server. You need to scale horizontally. Or you're building some application that needs to be up and running 24/7 and you want to have Postgres that never fails. One of the solutions in the Postgres ecosystem is YugabyteDB. YugabyteDB is a distributed SQL database that is built on the PostgreSQL source code. You can literally think about YugabyteDB as of a distributed Postgres. I've already deployed YugabyteDB on my local machine, and now I can connect to the database on this port number and show you the state of the cluster. I have 3 nodes running also in Docker. And to shorten the time, I created this movie table and I preloaded all the data, including all of those embeddings generated by OpenAI model. If I go to data grip, I can open a connection to Yugabyte. We are also going to use the same driver that is created for Postgres because YugabyteDB is just distributed Postgres. Let me test the connection to the database. Yep, the database is up and running. Refreshing this connection. And let me open the query console, where I just want to copy, paste, and execute the same query that we executed previously with Postgres. And here, as you can see, also different movies, descriptions, and overview vector. So generally, the YugabyteDB cluster is up and running. We have 3 nodes in this cluster. We can scale horizontally and we can withstand the various outages. But what needs to be done from the application standpoint? You will be surprised to see that all we need to do on the application layer is just to update the connection string. Let's go back to our Jupyter notebook and scroll to the beginning where we have this code snippet that opens a database connection. Here it is. That was our connection string. YugabyteDB is also running on my local laptop, which means that the local host remains the same, and we certainly can use the same Postgres driver for YugabyteDB. You can use Postgres as the database name or user. What I actually decided to use, I'm going to use YugabyteDB database, and the username is Yugabyte, and the password, guess what, is also YugabyteDB. So basically it's just changing the credentials. And finally, for YugabyteDB, you just need to change the port number because I have both YugabyteDB and Postgres running on the same machine, and YugabyteDB is listening on this port number. That's all I need to do. Let's run this request. I successfully connected just to Postgres to YugabyteDB right now. And now if I jump to my similarity search request, yeah, for instance, this one, where are we getting various recommendations and pre-filter the data. Let's run this request over the YugabyteDB cluster. And here, as you can see that, yeah, we've got exactly the same recommendations with YugabyteDB. And if you keep running, you can see that the latency is also very low. Generally speaking, you're getting the same result set, but right now you have a distributed PostgreSQL cluster that can store millions and millions of various embeddings, and that will never fail even if any database nodes go down. How do you like this, my friend? Isn't it cool? It literally took us a few minutes to get started with Postgres pgvector and Python. We learned how to perform the vector similarity search, how to pre-filter your data, how to create specialized indexes, and how to run your Python application over a distributed PostgreSQL cluster. And that's just the beginning. In the description to this video, you'll find the link to this Jupyter notebook so that you can reproduce all the steps on your end. And have fun mastering databases, my friend. Bye bye now.